The loops proposed in the previous video complete the alternate control configuration. A previous video also examined the tuning of the feedback trim controller for the hot air temperature. This video will tune the other three loops. The first issue is the order for tuning the loops. The characterization function was developed for a hot air pressure of 2.5 millimeters mercury. This suggests that we start by tuning the hot air pressure controller. Next, we tune the scrubber duct inlet temperature controller. The scrubber duct inlet temperature essentially determines the hot air flow by adjusting the opening of the fresh air damper. The hot air pressure controller quickly adjusts the hot air damper openings to compensate for any effect on hot air pressure. Finally, we tune the baghouse inlet temperature controller. As the hot air pressure controller is currently tuned, the controller gain is 4% to percent, and the reset time is 0.2 minutes. The reset time is the same as for the single loop configuration. A different value for the controller gain is to be expected. The hot air pressure controller is outputting to the hot air dampers instead of the fresh air damper. Switch the hot air pressure controller to auto. Change the set point from 2.5 to 3.0 millimeters of mercury. The hot air pressure, the green pin, responds very quickly. Change the set point back to 2.5 millimeters of mercury. Place the simulator on hold. Then expand the trend display to examine the hot air pressure in detail. The response is rapid and exhibits a small peak with a very short duration. For such a fast loop, there is nothing to be gained by refining the tuning. Restore the trend display to its original configuration. As the scrubber duct inlet temperature controller is currently tuned, the controller gain is 7.5% to percent, and the reset time is 0.5 minutes. The controller gain is large, but for a temperature loop, not unreasonably large. A reset time of 0.5 minutes may be too short. At least superficially, the scrubber duct inlet temperature controller has to contend with the furnace dynamics. For the single loop configuration, the reset time was 1.5 minutes. Place the simulator and run. Then switch the scrubber duct inlet temperature controller to auto. Next, change the set point from 80 to 85 degrees Celsius. The scrubber duct inlet temperature, the cyan pin, responds quickly with a small but acceptable overshoot. Change the set point back to 80. The response to the decrease is only slightly different to the response to the increase. Place the simulator in hold. Why the shorter reset time? In the single loop configuration, the scrubber duct inlet temperature controller relied entirely on the hot air temperature loop to maintain the appropriate relationship between the fresh air damper opening and the fuel gas valve opening. This is not the case in the alternate configuration. The quick-acting ratio controls are largely responsible for maintaining the appropriate relationship. The hot air temperature loop provides the feedback trim. The current tuning for the baghouse inlet temperature controller is a controller gain of 20% and a reset time of 0.3 minutes. The baghouse inlet temperature is the result of mixing two gas streams, so a short reset time is expected. The controller gain is large, but often encountered in temperature controllers. Place the simulator in run. Then switch the baghouse inlet temperature controller to auto. Next, change the set point from 70 to 75 degrees Celsius. The baghouse inlet temperature, the yellow pin, responds quickly with a small overshoot and oscillations that rapidly decay. Change the set point back to 70. The response to the decrease differs only slightly to the response to the increase. Place the simulator in hold. The performance of the alternate configuration is clearly superior to the single loop configuration. This video focused solely on tuning the controllers. The next video examines the responses for other aspects pertaining to the performance of the controls.